Chapter 9.3, testing the proportion P. And if you remember last time, we're still trying to do the same sort of thing. We're trying to think about the relationship between a sample and the population. And in this case, we're talking about the binomial probability. So we've thought all along about relationships. On the sample side, you have X bar, and on the population side, you had mu, and this means average, right? So you got the average from the sample, average from the population. We have S, which is the standard deviation from the sample, and sigma, which is the standard deviation of the population. And then finally, last time we talked about P, which represents the proportion. But when we talked about the sample, we put a little hat on it. I know it's confusing, and I didn't create it, but this is what we're dealing with. Okay, so we talk about a proportion, and what is that? That means we're having a binomial distribution. And so if we're talking about something binomial, where there are only two outcomes, and so if it's binomial with two outcomes, then P is the percentage of the time that the outcome that you're choosing occurs. So it's the percentage of time that you have a success or the percentage of time that you have a failure. So P is that proportion or percentage. So it's a number between 0 and 1. So P hat is that percentage you measure from your study, and P is the true percentage. Now, just like always, last time when we did a confidence interval, we used P hat to guess P. This time we're going to do a hypothesis test, and hypothesis tests, in some way you could think of going the other direction, and that is we say if we were given, if we have a given proportion that we would expect, say you expect a 50-50 proportion, what is the likelihood of your sample occurring? And if your sample is very unlikely, then that means that the proportion you started with is unlikely to have been a correct assumption. So we kind of do our hypothesis, which is this little dance. And let's go back, let's remember how we did hypothesis testing from before. So from before, our hypothesis looked like this. We had H naught, mu is equal to some number, and H1 was mu is either greater than, less than, or not equal to some number. And then we had our test statistic, and we found our p-value and did our conclusion. Hopefully this is good, this is making sense. You've done the quiz, you've been watching these videos, and you're on top of things. So now the only question is, how does this change if we talk about p's instead? So today, we're going to have a slightly different set of standards. So today, instead of doing mu's, our H naught is going to be that P is equal to some number. But notice it's kind of the exact same idea, because mu is the average result if you did a study. P is the proportion of successes, the percentage of time that something happens. It kind of feels a little bit like an average. So it's the exact same idea. We're only wording it just ever so slightly different, wording it with P's instead of mu's. And then our H1 is going to be that P is either greater than, less than, or not equal to whatever the number. So this works out the exact same. Now the test statistic ends up being slightly different, but if you pay attention, you'll see that it's just the same test statistic, but reframed in kind of this P language. It's still going to be a Z, because things that are binomial always have a really nice normal distribution. They kind of look nice and normal every time. So it's still going to be a Z. Instead of X bar, we're going to use P hat. Instead of mu, we're going to use P. So we're going to change those two letters, but we're still using this number here, and we're using whatever number came from our average right here, or came from our sample. So it's kind of the same relationship. And now when we divide, we don't have a standard deviation anymore, but what we have is that formula for standard deviation that we found a few sections ago. And that formula is P times 1 minus P. And then we divide all that by n. So it's the square root of P times 1 minus P over n. And so this ends up being our important formula that we're going to need to use to find our test statistic. Once we have our test statistic, we go about the problem the same as we have. So we still use the normal CDF, mu equals 0, sigma equals 1. We still find the p-value in the same way, and we still make our conclusions in the same way. So really, everything is the same, except for our hypotheses. We use p's instead of mu's, and our test statistic, we use p hat and p instead of x bar and mu. And then, but those really feel kind of the same. And then we have this new standard deviation instead of our given standard deviation. But it all, like I said, it all feels very similar. So let's work on a problem. If you're feeling on top of things, you might want to go ahead and try the problem before I do. However, if not, feel free to watch this first problem and then try the second problem independently. So let's start with problem 9.9 and see how far we can get. Okay, so 9.9, a television show makes a bold claim that pennies spun on their edges will land on tails more than 80% of the time. A math professor tests this by grabbing a 1963 penny, spinning it 320 times, and recording 294 tails and 26 heads. I have a confession. This is actually me. So there's a bit of a backstory here. I'm not going to go into it. It's too bad because it can be kind of entertaining. I was asked to be on a TV show, and the TV show made these claims about spinning pennies, and they wanted me to say if they were true or not. It actually is kind of a well-known thing in the math circle that pennies are more likely to land tails than heads when you spin them. It turns out that after the study, this is only true for really old pennies. It's not as true for new pennies. But okay, this is something that is kind of known in math circles. And so they wanted me to go on the show, and so I did. And they said, well, so the penny lands on tails 80% of the time. And I said, I don't know what percent of the time it is. And so I kind of got in an argument with the producer because they wanted me to say this and I wouldn't. And then they said, well, it lands on tails more often because the head side is heavier, right? And I said, I don't know why it lands on tails more often. I just know that it does. And again, we get in another argument. And what was interesting when the TV show finally came out, what they did was they just voiced over the part that so they said, does it land on tails more than heads? I go, yeah, it lands on tails more than heads. And then the voiceover guy would go, and in fact, it lands on tails 80% of the time. So the things I wouldn't say, they had the voiceover guy say for me, which has made me skeptical of everything I see on TV. So if you're ever watching, if you ever happen to be watching a show and there's an expert talking and then they take the expert off the screen and the voiceover person puts words in their mouth, there's a distinct possibility that the reason the voiceover person is saying it was because the expert wouldn't. So always have that radar on when you're watching TV. At any rate, after this experience, I decided to ask myself, well, what is true about spinning pennies? And so I got obsessed, and myself and a student spun thousands of pennies. Well, we spun, I think it was 30 pennies, but we had totals of thousands of spins by the time we were done. What we found is that really old ones do land on tails a lot of times, sometimes more than 80%. The ones that are newer don't show as much of an evidence. I then got obsessed. I went to the Denver Mint because I happened to be in Denver, and I peppered one of the tour guides with questions to the point that I really felt sorry for them, that they had to deal with all of my questions. But okay, so I spun thousands of pennies. By the way, a little bit of a forward look. You get to spin some pennies on your next quiz. So I'm going to let you do this experiment a little bit for yourself, and just see how it turns out. You don't have to spin thousands of them. You'll have to spin a few, but not thousands. Okay. A television show makes a bold claim that pennies spun on their edges will land on tails more than 80% of their time. A math professor tests this, that math professor is me, by grabbing a 1963 penny, spinning it 320 times, and recording 294 tails and 26 heads. So the question is, what we want to do is we want to test whether or not this shows up. So for our hypotheses, so we always kind of start these tests in the same way. So we'll start with our hypotheses. Our null hypothesis is that P equals 0.8, because that's what we're trying to test. So they made the claim that it lands on tails more than 80% of the time. So we're going to go 80%. We'll just make that our assumption and see if we can disprove that it's 80%. And so our alternative hypothesis is going to be that it's bigger than 80%. So when you read that problem, hopefully it makes a little bit of sense. At any rate, we'll now move on to our test statistic. So once you have your hypotheses set out, you're ready to start using your test statistic. And we're going to do that using that formula that we had earlier, which was p hat minus p divided by the square root of p 1 minus p over n. One place that I see that's easy to make a mistake, and in fact when I was prepping I wrote it wrong, is to put hats on the bottom. We don't put hats on the bottom because we're assuming that this is the actual probability. We're saying what's the likelihood of this occurring if this is the real probability for the entire sample. So if this is the real proportion, then this is the real standard deviation. So this is like a sigma standard deviation. Okay, so we'll use those numbers and we'll calculate it. And that means that z is equal to, and now I just have to put these numbers up. Oh, one thing I need to do is I need to calculate what p hat is because I don't know it yet. Well, p hat is just found by taking the number of successes divided by the total number in their proportion. And so we had 294 successes here with a tail being a success. And we had that out of 320 proportions. And so when I take 294 divided by 320, I get 0.91875. Okay, so 0.91875 is that number. And now what do I need to do? I need to go calculate all of that with my z problem. So I do 0.91875 minus 0.8, all divided by the square root of 0.8 times 1 minus 0.8, which is 0.2. These two just need to add up to 100. And then we divide that by 320. Careful when you type this in. It's all in the square root, including the 320. So just be careful that you get all that typed in the way it's meant to be. Okay, so now that we have that, we're ready to start calculating. And as I type this into my calculator, I get a number, and the number that I got is 5.31. So that's the number that I got there. All right, and now I'm ready to start moving along and look at what my answer is. So I've done my hypothesis, I've done my test statistic, so now I'm ready to find my p-value. And so for my p-value, I do just what I would expect, and that is I draw myself a normal distribution. I put this 5.31 on here, and then I shade this part. So I'm going to do normal CDF. For my lower, I'm going to choose 5.31. Notice I shaded the right-hand side because we have a greater than problem. It's a greater than problem. And then my upper is going to be like any really big number. I'll just put a whole bunch of 9s on there. And then I'll do mu equal to 0 and sigma equal to 1. And I'll type all this out, and I'll get my p-value. By the way, let's circle. I get my p-value, and my p-value is 5.49 e to the negative 8. Real quick note, if you, on a test or quiz or something, if you circle 5.49, I'm going to be very disappointed in this because this is not the right answer. It's not close to the right answer. And by the way, 5 isn't even a possible answer. The only possible answers are between 0 and 1. This is bigger. This is like saying 500%. That doesn't make any sense. What it is it's 5.49 e negative 8 on your calculator. What does that e to the negative 8 mean? It means you have to move the decimal point 8 spots that way. So that means you've got 1, 2, 3, 4, 5, 6, 7 zeros, and then 5, 4, 9 right here. So this is your number. So if you leave off this e to the negative 8, the number actually looks quite big. I mean, 5 is a really big number, but this is not a big number. This is super tiny. There's lots and lots of zeros. So now we're ready for our conclusion. What is our conclusion? Well, what we need to do is we need to compare that p with our alpha value of 0.05. And what we notice is that p is much smaller than alpha. I mean, p is almost 0. To the point, so what does that mean? That means we reject h naught. So the chance that the chance that the coin lands on heads or lands on tails 80% of the time is almost 0. The actual truth is that it lands on heads much more than 0, much more than 80%. So we're going to reject h naught. We conclude that the penny lands on tails more than 80% of the time. Okay, so that's just kind of how we think about this problem. Hopefully this is all making sense. What we want to do now is we want to jump over to problem 9.10. This is a very similar problem. This time I used a newer penny. I used a 2007 penny, which at the time I did all the spinning was really quite new. I think it was around 2010 when I did all my spinning. So we'll do 9.10. And this is a time when you should pause your device and try this problem independently and see if you can successfully do it. So as I erase my boards, pause your device, try the problem, and see how much success you can have. All right, well, hopefully that went well. Hopefully you did really well. If not, that's okay. We're still learning. So what are we going to do? We're going to start with our hypotheses. Let me just not even worry about labeling all of these. So what are our hypotheses? H naught. Well, notice the problem says we want to know that if they land on tails more frequently than heads. Notice we didn't give them, we didn't say 80%, 75%. We just said more frequently. What does more frequently mean? More frequently would mean 50% of the time. So our default is that they would land on heads and tails the exact same amount. What we want to test is whether it's greater than 50% of the time. So there's our problem. Now what we need to do is we need to go get that test statistic, which we wrote earlier, p hat minus p divided by the square root of p 1 minus p over n. Again, the book likes to use q for that. And then I need to figure out, well, what is the p hat for this problem? And p hat is going to be number of successes divided by total number. Notice this problem had 430 successes and then 808 total spins. So that's our p hat. So let's calculate that in our calculator. 430 divided by 808, and we end up with 0.532. So 0.532, you could add more decimals. That seems reasonable to me. Okay, so in our experiment, our sample, it landed on heads 53% of the time. All right, so let's come over here and calculate our test statistic. So our statistic is 0.532 minus 0.5. That's just that number right there. And then we divide by the square root of 0.5 times 1 minus 0.5, but that's also 0.5. So 50% and 50% match up with each other, divided by 808. We type all this in your calculator. Hopefully you're successful at that, and we get 1.829. 1.829. Okay, so that's what we get for our test statistic. So now we're ready to move on down to part C. And part C is finding the p-value. So for a p-value, I'm going to draw the exact same picture I've always had. I'm going to put 1.829 on here and shade to the right. Use normal CDF because we're looking for greater than. Normal CDF will have the lower is going to be 1.829. The upper is just any really big number. And again, always mu 0 and sigma 1. Okay, so we calculate all that out. And if I did it correct, I got 0.033 for my p-value. Now we're going to compare this to alpha equal to 0.05. And what do I notice? I notice that p is smaller than 0.05. So I get that p is less than alpha. So I still have a small enough. So what does that mean? That means I reject H naught. So my hypothesis that they land on heads and tails an equal amount of time is not true. Instead, we reject H naught. And so therefore, what does that mean for our test? That means our penny lands on tails more than heads. There's evidence that they don't land on heads and tails equally, but that it does land on tails more often than heads. Now, I want to make a quick observation. This is a good point to talk about a difference that we have in the world of statistics. And that difference is called the difference between statistical significance and practical significance. So what we see is that there's a statistical significance in this problem, and that is that our pennies definitely show up on heads more or land on tails more than heads. But how much more? The answer is not much more. And if you were to go create a confidence interval, what you'd find is that the probability of landing on tails is probably somewhere around 0.5 to 0.55. So somewhere between 50 and 55% is somewhere in there. It's actually quite small. So your probability of landing on tails is a little bit bigger than heads, but not a whole lot bigger than heads. And so this is the difference between having statistical significance, which says that it's more, and having practical significance, which means that it's enough more that it actually means something out in the world where you're trying to do your problems. And one point that we can make is that whenever you're doing math, a lot of times it's easy to prove things statistically, and that is a math job. To prove that things matter practically is the job of a human. That's kind of why we need people to interpret and read these things. Okay, maybe that makes a little bit of sense. The truth is, right, so if you spun a penny enough times, even if it was fairly balanced, if you spun a penny 10 million times, it might show up on heads like 0.501%, and tails maybe tails 0.501 and heads 0.499, and you might still get statistical significance even when practically the difference between 50.1% and 49.9% doesn't really make a meaningful difference in any sort of practical way. Quick side note, there's one last thing you should take away from this problem, and that is how to cheat your friends. Something we always try to teach our students here at LCU. Okay, I hope you get that that's a joke. We don't want you to treat your friends. But at any rate, if there's something really important that you want, maybe what you should do is keep an old penny in mind. So old pennies consistently land on tails more than heads. So go find an old one, 1960s, somewhere around there, and just keep it with you. And then when you and your friend are debating, like say you're saying, which restaurant are we going to go to? And you have one that you really want to eat at. They have one that they really want to eat at. Of course, we can't eat anywhere right now because of the world we live in. But when we all get back to normal, what you do is you debate and you go, okay, here's what we'll do. We'll spin my penny. If it lands on tails, we'll go to my restaurant. If it lands on heads, you go to your restaurant. Your friend will go, okay, sure. And you spin it and it lands on tails. And you go, oh, look at that. It just happened to go my way. And you take your penny and you win. And what your friend doesn't know is that you actually had about a 90% chance of winning that spin, and your friend thought it was about a 50-50. So there you go. So there's a good way to maybe not cheat your friends, but maybe influence probability to get the most out of it. All right, good luck. I hope this goes well. And one last note is section 10.3 we will be skipping. So 10.3 is where we take all of these problems and we add a second variable. It's actually very similar to where we did the two variable problems earlier. And I just decided that this is one of those items from the semester that even though I love it and it's really interesting, just for the sake of time and for the sake of us studying at home, that we can skip this and move on. So the next series of videos will be from chapter 11, and what we'll be talking about is linear regression. Oh, no, chapter 4, sorry. We'll talk about linear regression, and that is what happens when you have two variables that are related to each other, and can we make a scatter plot and draw a line of them and those things. And I think this will be super interesting. So I'll see you then.